Welcome. We are about to begin chapter 13, looking at compounds and aqueous solutions, and we're going to be continuing dissolving substances in water. And along with substances that dissolve in water, sometimes we create some ions in solution. And a little joke I came across here was actually, what did one ion say to the other? And it was, "I've got my eye on you." Pretty good, guys, when we're talking about aqueous solutions of electrolytes and non-electrolytes, and a few definitions here that you need to get down. Just pause the video right now and copy these definitions down real quick here. You need to know dissociation, ionization, and the difference between the two forms of ions from a molecular compound. It is kind of a good note to make there. And then as a quick review, we're going to review here ionic and covalent compounds. Remember that an ionic compound is going to be your metal and nonmetal, whereas a covalent compound is your two nonmetals that are going to be sharing electrons. So the point here that we need to understand is, what does dissociation really mean when we're talking about the separation of ions that occur when an ionic compound is dissolved in water? And we're going to look at a few examples here on the next page. So let's go ahead and look at a few of these compounds here, and let's see if we can distinguish whether they're an electrolyte or a non-electrolyte. Remember, an electrolyte is a substance in water that conducts electricity because it completely dissociates or ionizes in solution. Whereas a non-electrolyte does not conduct electricity because it does not completely ionize, or only partially does, or it is not going to dissociate whatsoever in solution. So the way that we can kind of identify whether each one of these compounds is an electrolyte or a non-electrolyte is really look at its chemical bonds. So here we have sodium bromide, and we see sodium, it's right here in group 1, and bromine is over here in group 17. So this is a non-metal and that's a metal, and it's going to be classified as an ionic compound. So we would typically see that it's going to completely dissociate. So it's going to be an electrolyte. And I'm just going to put EL for electrolyte and Ne for non-electrolyte. And then the way that we actually end up writing this is NaBr, when put in water, AQ, so AQ, remember, is aqueous, put into water, is going to dissociate into Na plus and Br minus. It's going to break up into its ions with their respective charges. Now, this might be a good point to go back and remember that the charges are +1, +2 for group 2, +3. Group 4 is weird because it does the range, negative to +4. So it has that range. Whereas 5, and now they're all trying to get to the noble gas stage, which is 0 for its charge because it has a complete full valence electrons. So at 5, they start gaining electrons, so it becomes -3, -2, -1. So this is a good refresher here for you to have on the charges that typical ions form on the periodic table. So let's look at NO2. We have N as being a nonmetal, oxygen being a nonmetal, so it should be a covalent compound. And I'm kind of classifying this by the type of compound here. So covalent compounds typically are going to be your non-electrolytes. And we say that in a solution, if NO2 for whatever reason were put into a solution, that it would not dissociate. It would stay as NO2 in a solution. Our next is calcium chloride. Calcium's here as a +2 charge. Chlorine is over here as a -1 charge. So that's a metal, non-metal transfer of electrons, so it is an electrolyte. And in water, calcium chloride, AQ, will typically completely dissociate, so calcium +2 and chlorine -1. But how many chlorines do I have here? 2. So then that means over here I need to put a coefficient of a 2 chlorine ions in my solution will form. Here we have a polyatomic ion, ammonium, and another polyatomic ion, nitrate, so ammonium nitrate. Remember, even though the NH4 and NO are all nonmetals, N and O are nonmetals, and remember hydrogen, it's up here, it's not written in, but it's a nonmetal as well. They still have charges. Remember, the ammonium ion is a +1 charge, and the nitrate ion is a -1 charge. And since they're polyatomic ions and they still have charges, we can kind of classify it as an ionic compound. Sometimes you see them classified as both ionic covalent compounds, but we can still kind of say since it has charges, it'll be an electrolyte. So my ammonium, NH4, and nitrate, NO3, when placed in water, AQ, will dissociate into NH4 positive and the NO3 negative as your ions in solution. And next I want to show you a short clip that really helps emphasize this point of dissociation of ions in solution.
When a substance dissolves in water, we say it's aqueous. Thus we write the formula followed by AQ. For example, if calcium chloride is dissolved in water, we represent this as CaCl2AQ. An aqueous solution of calcium chloride conducts electricity very well, which means that it exists nearly completely as dissociated ions. We can write an equation for the ionization of aqueous calcium chloride as CaCl2AQ arrow Ca2 plus AQ plus 2Cl minus AQ. The single arrow means that the solute dissociates completely or nearly completely in the solvent water. Notice that the subscripts in the formula become coefficients when we show the ions separately. It is appropriate to represent strong electrolytes either by the molecular formula followed by AQ or as the separated ions. For example, CaCl2AQ or Ca2 plus AQ plus 2Cl minus AQ. Sugar dissolves in water, but it does not conduct electricity. This is an example of a non-electrolyte. To indicate that it dissolved in water, we write C12H22O11AQ. Since it does not dissociate, we do not need to write an equation. Acetic acid or vinegar also dissolves in water. Thus we write its formula as CH3COOHAQ or C2H3O2HAQ. Recall that when a weak electrolyte, like acetic acid, dissolves in water, it conducts weakly, which is one piece of evidence that tells us that a small amount of molecules breaks apart into ions. We can write the equation in the following manner. CH3COOHAQ double half arrows CH3COO negative AQ plus H plus AQ. The double arrow is used to indicate that the reaction can go in both directions. Because of the poor conductance, we know that the majority of the solute molecules exist as acetic acid molecules, while only a few break apart into the respective ions. In order to maintain these concentrations, if another acetic acid molecule breaks apart in the solution, then somewhere else in the solution, an acetate ion and a hydrogen ion recombine to make a molecule of acetic acid. It is important to note that in the case of weak electrolytes, such as acetic acid, we tend to represent it the way the majority of the chemical species exist. In this case, we would write the formula as CH3COOHAQ or C2H3O2HAQ. This represents that the majority of the dissolved acetic acid exists in molecular form.